You know how it is in tech, right? We are always chasing the next big thing. New frameworks, new languages, new architectures. It never stops. But what if I told you that the biggest, hottest debate in data systems right now isn't actually new at all? What if we've literally been here before?
So check this out. The legendary computer scientist Alan Kay once said that computing is basically pop culture, and that pop culture has a disdain for history. Now, I want you to just hang on to that thought. Keep it in the back of your mind because trust me, it's going to come roaring back by the time we're done here. Okay, let's just dive right in. If you're a developer, this probably looks painfully familiar. You're just constantly getting hit with buzzwords, right? NoSQL, big data, web scale. It feels like this never-ending flood of new tools and ideas, and honestly, it can be totally overwhelming.
But here's the thing. Underneath all that noise, what most of us are actually building these days are what we call data-intensive applications. And the key takeaway here, and this is super important, is that for most modern software, the bottleneck isn't the CPU anymore. It's not about raw processing power. The real challenge is the data itself. Its sheer size, how complicated it is, and how quickly it's always changing.
So, okay, if data is the main problem we're all trying to solve, how do we build systems that are actually good at it? Like, how do we even measure if a system is a success or a failure? Well, it turns out it pretty much all boils down to three big ideas, these three fundamental pillars of design.
And those three pillars are reliability, scalability, and maintainability. Together, they give us this really powerful way to think about and judge pretty much any data system out there. So let's quickly break down what each one really means.
All right, first up, reliability. And this is a big one. It doesn't mean nothing ever breaks. Come on, we know things are always going to break. What it does mean is that the system as a whole keeps working correctly, even when parts of it go wrong. So the goal is to build something where one component failing, like a single server dying, doesn't take the whole ship down with it. Next up, we've got scalability. And please, don't think of this as just a simple yes or no thing. It's not a checkbox. Scalability is really a question we have to ask ourselves. If our traffic doubles tomorrow, what's our plan, right? How are we going to handle that growth? What's our strategy to keep performance from just falling off a cliff? And here's a perfect, totally wild example of what load can look like in the real world. Think about Twitter. The scaling challenge for them isn't just about how many people are tweeting. It's this thing called fan out. So one celebrity posts one tweet, and that can trigger this insane cascade. We're talking over 30 million separate writes to update all of their followers' timelines. That is a very specific and very, very challenging kind of load to deal with.
And speaking of performance, you have to be so careful about how you measure it. Just looking at the average response time can be incredibly misleading. This chart here shows you exactly why we need to look at percentiles. I mean, your average might look fantastic, but the 99th percentile, that's the experience of the slowest 1% of your users, could be absolutely terrible. And guess what? Those users who are having the worst time are often your most engaged, most valuable customers.
And finally, our third pillar, maintainability. And I gotta say, this is truly the unsung hero of good system design. It's so easy to forget that the real cost of software isn't writing it the first time. It's in the months, years, even decades of keeping it running, fixing it, and changing it. So building something that's easy for other humans to work on, something that's simple and can evolve, it's absolutely critical.
All right, so now that we have that framework in our back pocket, reliability, scalability, maintainability, let's get to the main event. We're talking about the central conflict that has pretty much defined the world of data for the last decade plus. In this corner, the traditional relational model, and in the other, the challenger, the newer document model.
So where did this whole fight even come from? Well, it was born out of this really annoying problem called the object-relational mismatch. See, most of us developers, we write code using objects, but old-school SQL databases, they think in tables and rows. It's like they speak two different languages, and that constant awkward translation back and forth, it created so much friction that it basically fueled the entire NoSQL movement.
Let's make this real with an example. Imagine a LinkedIn profile. In the classic relational world, you'd chop that profile up into little pieces. You'd have a table for users, another table for their jobs, a different one for their education history. You get the idea. And they're all linked together by a user ID. So if you want to see the whole profile, you have to do this operation called a join to piece it all back together.
Now the document model, it throws that whole idea out the window. It takes a totally different approach.
The entire LinkedIn profile gets stored as one single self-contained thing, a JSON document. And what's cool about this is that the structure of that data can perfectly match the objects you're working with in your code. It just feels so much more natural, and you get to skip all those complicated joins.
So, as with everything in engineering, it's all about a trade-off, right? On one hand, relational databases are the undisputed kings of joins and making sure you don't have the same data copied all over the place. On the other hand, document databases give you this awesome data locality. Everything about one thing is in one place, which solves that mismatch problem. But there's always a but. The big catch has always been that they're just not that great at handling relationships and joins.
And this right here, leads us to the critical question, the one that really starts to show the cracks in this simple document model. What happens when your data isn't just a nice, neat, self-contained little package? What do you do when things get more connected?
Let's see how this actually plays out. Go back to that LinkedIn profile. Think about the company name, say Microsoft. If you just store that as plain text in every profile, you're going to get typos, different spellings, and if they ever rebrand, good luck updating that everywhere. It's a nightmare. But if you treat Microsoft as its own separate thing with its own ID, suddenly you get consistency, and you can easily link out to a full company page. But see, here's the problem. Doing that creates many-to-many relationships, which is the exact thing these document models have a hard time with.
And this is the moment where our whole story takes a really sharp turn. We're about to jump in a time machine. Because it turns out this whole modern debate, well, it might not be so modern after all.
So let's just ask the big question head-on. Is this fight that we're having right now, the one between the document model that's great for simple, nested data, and the relational model that's great for highly connected data, is any of this actually new? To get the answer, we have to go way back. We're talking the 1970s, long before SQL was king. Back then, the most popular, dominant database in the world. We're talking something used for everything from the banks on Wall Street to the Apollo space program, was a system from IBM called the Information Management System, or IMS for short. So how did this powerhouse database, IMS, actually structure its data? Well, it used something called the hierarchical model. And what that means is that all the data was basically a tree of records, nested inside of other records. It was amazing for one-to-many relationships, but it really, really struggled with many-to-many relationships. Starting to sound a little familiar? Okay, get ready, because here is the big aha moment. The parallel here is it's unmistakable. If you look at the structure, a modern JSON document is a hierarchical model. It is essentially the same exact idea as a record from that 1970s system. The very problem that we are all arguing about today on Twitter and in conference talks, it's the same problem engineers were dealing with 50 years ago.
I mean, look at this timeline. It just lays the whole cycle bare. In the 70s, the hierarchical model hits a wall because it can't handle many-to-many relationships. So in the 80s, the relational model is invented, and its whole reason for being, its killer feature, the join, was created specifically to solve that exact problem. And now, fast forward to today, and we've basically brought back the same tree structure with document databases, and in doing so, we've brought back the exact same limitations.
And that brings us full circle, right back to what Alan Kay said about our disdain for history. So if the relational model was the big solution to this problem 50 years ago, what does it say about us that we're now challenging it with what is essentially the same old idea just wrapped up in a shiny new package? What did we forget? Or maybe a better question is, what new problems are we trying to solve now that make this whole cycle worth repeating? And that's the billion-dollar question for the entire future of data.